All right, last video for stoichiometry is looking at acid-base titrations. So acid-base titrations are a very important lab skill. Normally we do 3 titrations in Chem 20. You do several titrations in Chem 30. If you take any first-year chemistry courses, you're definitely going to do titrations then. I remember doing titrations all the way through university, so first year, second year, third year, fourth year. So they are very much a skill. They are something that theoretically you hear about and you're like, oh yeah, like that sounds super easy. And then trust me, you go to the lab and you do it and you are about ready to hurt your lab mate for ruining your titration. You can ask anybody who took Chem 20 last semester. They will definitely remember doing titrations, but what they'll also remember is that once they had done it quite a few times, they figured out how to do it, right? That's why it's very much a skill, right? Generally, you're not great at something the first time you try it, but the more you practice, the better you become. There's usually that one person, maybe 2 people that just kind of has the magic touch and can make it go really well. But I can tell you, I'm definitely not one of those people with the magic touch. I have like the worst hand-eye coordination, and I'll go to stop the titration, and instead of turning it off, I'll open it like full tilt, and then it'll be ruined, and I have to start all over again. So definitely a skill that requires a lot of patience. So the point of an acid-base titration is generally that we have one solution that we know the concentration of, and another one which we do not know the concentration of, and we are trying to determine what it is. So why we start with acid-base titrations is because we know when we reach a certain point, and that's because acid-base reactions are neutralization reactions. We can determine when a solution reaches neutral by measuring the pH or by using an indicator that's going to change colors around 7, okay? So here's our general experimental setup for what we're going to have if we do a titration. So we would start with our retort stand. We would obtain a burette clamp, which goes onto the retort stand. It just kind of slides onto the top, and then you screw this little screw in. Then we have a burette. So a burette is this very long, skinny glass tube. Okay, you'll notice it has all these little tick marks on it. And that's because it has the ability to measure, okay? All of these marks represent different volumes. You find way up here at the top, there's a 0 mil, and down here it stops at 50 mils. So generally burettes are used to add quantities somewhere between 0 and 50 milliliters. Okay, down here, they have this little valve. Okay, this valve opens and closes to allow for you to release solution. So when this valve, right now it's in the closed position because it's like this, but when we turn it to be like this, then it's open. And the solution is going to come through that burette and it's going to fall into our Erlenmeyer flask down here. Okay, we generally put what's known as the titrant into the burette. Usually this is the one with the known concentration, but sometimes when we start dealing with things, especially in redox, when you're in Chem 30, we sometimes kind of switch it around just because of the color changes that we are looking for. So what you're going to find, generally what you would do if you were actually in the lab doing this, is inside of this Erlenmeyer flask, we would generally be asking you to use a pipette and pipette in 10 mils of acid. Okay, I'm going to link you guys to a video when this one is done that kind of shows you how to actually do a titration. But yeah, you would use your pipette with your little blue bulb. Again, we never got a chance to use these in the lab, and it's very much a skill to do that. So I guess your best comparison to something you guys may have used before is like a turkey baster, right? It has the long skinny part, and then it's got the bulb that you squeeze. The difference is usually the metal part gets replaced with what we call a pipette, which is a glass tube with measuring amounts on it. And we have to make sure that we get a very precise volume inside of it. So in that last solutions unit, you definitely had a little video to watch on how to pipette. So yeah, we would use a pipette to collect 10 mils of acid, which we would then place into this Erlenmeyer flask. Acid, generally a clear colorless solution. We would be filling our burette with base, which is also a clear colorless solution. So what we are going to add to the acid in our Erlenmeyer flask is usually 3 drops of indicator. The reason we're going to do that is we need to know when to stop adding base. If we don't know when to stop adding base, we're just going to keep adding and empty the entire burette and be like, okay, now what? Nothing happened. It's still a clear colorless solution. So we're going to add a little bit of indicator into this Erlenmeyer flask so that we can see a color change, okay? So pipette 10 ml of acid into the Erlenmeyer, you're adding 3 drops of indicator. Your burette, generally you want to rinse it with a little bit of base first, dump that out, and then you want to fill it. Usually when we fill it, because it's a super skinny opening at the top, we're going to use a funnel up here so that it's a little easier to pour our base into it. Because if you try to pour a base into this teeny tiny little hole, you're going to make a mess of the lab bench end of yourself, okay? So when we fill it, we're usually going to fill a little above the fill line. And the reason for that is we need to fill this tip with a bit of solution as well. So after we rinse it, we're going to fill it more than we need, and then not into the Erlenmeyer flask, but into like a little waste beaker. We'll put that underneath, and we'll just open the valve a little bit to drain it so that that little tip gets filled with a little bit of solution. Once we've done that, then we are ready to start our titration. So when you are doing this titration, like I mentioned, you're going to put a carefully measured amount of solution into that Erlenmeyer flask along with your indicator, right? Generally for us, it's going to be 10 mils of whatever sample we're using. Into the burette, you place your titrant. That's your standard solution with a known concentration. Okay, we put that into the burette because the burette has those nice marks that's going to allow for us to measure how much we have. So because these are acid-base reactions, we know these are neutralizations. We know that we should be producing a neutral solution, right? When we have equal moles, which is what we're ultimately looking for in a titration, and we're looking for equal moles because generally when we balance those acid-base reactions, right, normally we're going to have our acid plus our base, and that's going to give us water, whatever our ionic compound is, right? So if we start with acid in our flask, we're going to start with an acidic pH. As we add base to it, we're going to find that that pH should start to rise a little bit. When we reach the point where these are present in the right ratio, I should have a neutral solution because water is neutral and my ionic compound is neutral. So I should have a pH of 7. If I add too much base, well, my pH is going to be greater than 7 because bases have pHs greater than 7. So really what we're looking for is to hit that perfect 7 pH. So that brings us to 2 important terms, equivalence point and end point. So an equivalence point is when our moles are equal, right? So when I look at this equation here, right, HCl plus NaOH, it all balances with a 1. So when I am at my equivalence point, I have an equal number of moles of HCl as I do to NaOH. If I'm not at my equivalence point, then I'm going to have more of HCl than I do of NaOH, or vice versa, okay? So equivalence point is when my moles are equal. In the case of an acid-base titration, when these moles are equal, I don't have any of that left. I only have water and sodium chloride, and I should have a pH of 7. So this brings us to end point. So generally when we do a titration, the only way I have of knowing that my pH is 7 is because an indicator changes color for me. We do sometimes use pH meters, and then we'll actually see that the meter will read 7, but a lot of times we use an indicator. And that's where end point comes into play. So when we use an indicator, there's a couple that we generally use. We tend to use, I think this is on the next slide, either phenolphthalein, bromothymol blue, or phenol red. And that's because these all change somewhere near 7. Okay, bromothymol blue is probably the best example of that, right? If you look up bromothymol blue in your data booklet, right, going back to that indicator table that we talked about before, right, you should find that between 6 and 7.6, it changes from yellow to blue. So if you think about the fact that we're making a neutral solution, 7 is kind of smack dab in the middle of these 2 colors. So I would know that I have created a neutral solution because I would see a color that's between yellow and blue, right? So I would be looking for green because green is the color in between yellow and blue. Okay, phenolphthalein is also one that's commonly used. When we're using phenolphthalein, we're looking for the lightest hint of pink. When you look at phenolphthalein in your data booklet, phenolphthaleins start to turn pink at 8.2. Some of you might be like, well, why would I want to use 8.2? I'm looking for 7. And we'll talk a little bit further in the lesson when we look at titration curves of why you can still get away with phenolphthalein as long as it's a really light pink. If it's a dark pink, you've done what we call overshoot the endpoint. So I was talking about endpoint before I switched over to this slide. So what endpoint is when the indicator changes to that color, right? So if I was doing a titration with bromoethanol blue, my solution would start yellow, and I would add base until I saw that it wasn't yellow anymore and it was green. And when I see green, because that color corresponds to the pH I'm looking for, that is when I would end my titration. Okay, that's why it's called an end point, because the indicator color change is telling you to end or stop your titration. So ideally, you have picked an indicator that is going to change colors right around where your equivalence point is, right? If I were to pick like methyl violet, let's say, which changes between 0 and 1.6, that would not be a helpful endpoint at all, because it would never change colors, right? Because it's not changing near 7. So equivalence point is when your moles are equal. End point is when your indicator changes colors. Normally, like I say, we choose indicators to try to make sure that that endpoint is going to match up as closely as possible with that equivalence point. So one thing you find with indicators is they change colors really quickly. It's going to be yellow 1 second, and then it's going to be blue. So generally when we do titrations, we do multiple trials, and we do multiple trials for a variety of reasons. So the first trial we generally do is just to get a ballpark idea of how much I need to add to my 10 mils, because initially I have absolutely no clue how much I need to add. So generally what we do in our first trial is we add 5 mils, and then we close the valve, we swirl it around, we check to see if it changed colors. If it didn't, we add 5 more mils, we close it, we swirl it around, check to see a color change. And we keep doing that until the color changes. Sometimes I don't have to do a full 5 mil increment, right? Maybe I'll have gotten to 10, and then I'll be adding, and then all of a sudden I'll be like, whoa, that totally changed colors, and I'll stop before I hit 15. But then that narrows down my range, and I can be like, okay, well, I know it didn't change in my first 10 mils. So when I go to do my next trial, where now I actually have an idea what I'm looking for, I can add those first 10 mils in one big, just open it and let it run. I hit 10, I close it. And then what I'm going to start to do is go a lot slower. And the reason you need to slow down is those indicators change colors so quickly. And if you just like literally let it run, you're going to go past green every single time. You're going to be like, it went from yellow to blue and I never saw green. And so then you actually would have no usable data. So generally what we do is that first trial, there's someone's car alarm, gives us an idea of what volume we need to have. And then when we do our second trial, all right, took a little pause break to let the car alarm stop. Well, I don't remember what I was saying now. So yeah. Then what you'll do when you're actually ready to do is you'll add that first bit in one big quantity. Then you're going to start to really slow it down. Maybe you're going to go drop by drop. So you're going to open it just a little bit. You're going to let that drop fall. You're going to close it. You're going to swirl it. You're going to be like, am I still good? Am I not? You will find when you get really close to that endpoint, you start having to add partial drops, because one drop is going to be too much. Okay, and again, this is really hard to explain without actually being able to show you. But generally what you want to do is open the valve a little bit, just so that like a little bubble starts to form on the end of your burette. Then you pick your Erlenmeyer flask up and you basically tap it on the side inside your Erlenmeyer flask, and that will transfer that partial drop into your flask. And then very carefully, you would take your Erlenmeyer flask and you would tilt it on the side and you would try to incorporate it inside of there. Again, very much a skill, takes a lot of practice. You will definitely find that when you take Chem 30 next year, I would strongly recommend when you get to titrations, you make sure there is somebody in your group that took Chem 20 in first semester and actually did a titration. because you don't want to wind up where everybody in your group is like, I've never actually done this. We will do a review titration, but it'll be one of those where other classmates will have already done it 3 times and you will never have done it before. And obviously it's a skill you want to learn. But yeah, having at least one person in your group to kind of be like, oh no, like this is what you do, this is how it works, to be like, oh, okay, I see what's happening, right? So maybe they show you once and then you try once and then someone else tries the next time, kind of thing. So, and then you are basically going to try to get 3 or 4 titrations in a row, not necessarily in a row, but before class is over, where you get some pretty similar numbers. Ideally, we're looking for that volume that you have added to be about 0.1 to 0.2 apart from each other. If it's more than that, then you probably really overshot that endpoint. We're also looking for like that consistency of colors. So if we're using phenolphthalein, we're looking for that lightest hint of pink. If we're using bromothymol blue, we're looking for green. Phenol red is another one you can use as well. We don't generally tend to use it very often just because 2 indicators is usually enough for you guys to practice and try with. Okay, so if you actually did a titration, this is generally the type of data you are going to collect. So you'll notice how we've got this data table. It has 4 trials, okay? And that's because we want to do multiple trials. We know when we do experiments, we're not accurate every single time. Things go wrong. So by doing multiple trials, what we can do is kind of look to see, do we have any data that doesn't line up with the others? And if we do, then we're going to omit that. We're going to recognize that it's an outlier. If they're all pretty consistent, then we would go ahead and use all of them. So here we have in the titration of sodium hydroxide with 10 mils of 0.2, I'm assuming it says moles per liter and it's just kind of off the screen. Yeah, hydrochloric acid, the following information was collected. Okay, so we have our trial 1, trial 2, trial 3, trial 4. Whenever you have multiple trials, you're almost always going to find that one of those trials needs to be omitted. So how you decide which one to get rid of. If it tells you colors, look for the one that isn't like the other. So light pink, dark pink, light, light. I want to get rid of trial 2. If it didn't give me colors and it gave me volumes, I would look at the numbers. And let's say it was like 12, 12.1, 12.2, and then like, I don't know, 12.7. Then I'd be like, oh, 12.7 isn't like the others, and I would get rid of that one, okay? So multiple trials, you're almost always going to get rid of one. It's pretty rare that you would leave all of them. Occasionally that happens, but yeah, definitely kind of as a general rule of thumb, you're always looking to try to get rid of one of them. So once we get rid of one, our next step is going to be to look at these different trials. So you'll notice that they've given us initial readings and final readings of burettes. So again, if we had actually done this lab, that also makes this a lot easier. But yeah, with that initial and that final reading, what we actually need to know is how much did we actually use. Okay, how we figure out how much we used, we just get the difference between the initial and the final. So that means we have 12.5 milliliters, right? And it's milliliters because when we look here in our data table, it said milliliters for this one. For the next one, we are going to do 37.9 minus 25.5, and we are going to get 12.4. So here, 12.4 milliliters. Okay, and then we're going to do the same for the last one. We're going to do 13 minus 0.5, and we're going to get 12.5 milliliters for that. Okay, so what we need to do is we're going to average these. Okay, we don't want to do 3 calculations to calculate the same thing. And average at the end, it makes more sense to average at the beginning. So we're going to average those volumes to figure out how much we actually used. So 12.5 plus 12.4 plus 12.5, divide by 3. So we get that the average volume is going to equal 12.4666, and that's going to keep going milliliters. Okay, same as before, I don't want to round because I'm not actually done my calculation. Okay, so once I have this, this actually becomes just like any other solution stoic question. It's not any different from that. Okay, the only different piece was really where this data came from. But after that, it becomes a normal solution stoic. So we titrated sodium hydroxide with hydrochloric acid. So sodium hydroxide with hydrochloric acid. Okay, this is going to give us water and sodium chloride. Okay, everything balances with a 1. We don't need to do anything else. Okay, so givens-wise, 10 mils of 0.2 mole per liter hydrochloric. So we know for hydrochloric it was 0.010. How many decimals? It did 0 liters. And the concentration of that, I don't know how I rotated that. Hold on, let me try to undo that. Oh no. All right, fix it. So 0.0100 liters, and it is a 0.200 mole per liter solution. Okay, for the sodium hydroxide, we have the volume. This was in milliliters, so we need to convert that to liters. So 0.01246, I'll keep going, liters. Right, and we are looking for the concentration of this, so that is our unknown. And now we're just doing some regular stoic. So concentration of sodium hydroxide is going to equal, start with that ratio, so 1 mole NaOH over 1 mole HCl. Right, that places our moles of NaOH. We need to get rid of moles of HCl, so we're going to times by 0.200 moles HCl per liter. Okay, this isn't the liters we actually want, right? This is liters of HCl. So then we are going to times by that 0.0100 liters, put that over 1. Okay, so now take a quick moment to look at our units. Moles of HCl are gone, the liters of HCl are gone. Last thing we need to do is put in that liters of NaOH. You also could have chosen to start with that liters, it really doesn't matter. And we would do times 1 over, and then here 0.01246, making sure again that you are using that entire number on your calculator and not actually rounding it. So what are we going to get? 1 times 0.2 times 0.01 times 0.01. Well, actually I should use my answer button. 2, 4. Okay, so did I do that right? I'm getting a very small number. No, I did not type that in my calculator right. Hold on. So 1 times 0.2 times 0.01 divided by 0.0124666. There we go. That makes more sense. Okay, so we are getting 0.160 moles per liter. Okay, 3 significant digits, because both of these had 3 significant digits. And when we look here, all the calculated values had 3 significant digits because they all went to 1 decimal place. Okay, so when you're given the data table, you're going to generally eliminate one that isn't like the other, either based on color. If it didn't give you color based off volume, you're going to average the remaining trials, making sure you recognize that that is always going to be in milliliters, what's giving you in that data table, never in liters. And then you're just going to do your little stoic calculation that looks exactly like the stoic calculations you did in solution stoic. Okay, so here's one more example. Basically is the exact same thing. The only difference is this one didn't give you an entire data table, instead it just gave you 1 trial worth of data. Okay, but we're still going to start by doing the same thing, which is to write that balanced equation between HCl and NaOH. Okay, this is going to give us water and sodium chloride. Okay, givens-wise, we were given the volume of HCl as that 0.02000 liters. And then for the sodium hydroxide, just spread this out a little more to give a little space between those givens, we were told that it was a 0.100 mole per liter solution. And okay, volume-wise, the volume here is a little bit different because it gave us an initial and it gave us a final value. So we're going to have to subtract them. So we're going to do 36.3 minus 0.2. So from there, we get that our volume is going to be 0.03610 liters. Okay. So we're looking for the concentration of HCl. That is our unknown. So now we do our unit analysis. All right, these videos are eating into my disk space. Had to delete some stuff. Okay, so from here we are just going to go ahead. Oh, where am I writing? Where's it typing? Way over here. That's not where I want to be typing. We are going to calculate the concentration of HCl just using our unit analysis. So we are going to do 1 over that 0.02000 liters, right? So that we are placing liters of HCl on the bottom because we're looking for moles per liter of HCl. We are then going to times by our ratio, so 1 mole of HCl over 1 mole of NaOH, right? So now we've placed the moles of HCl. We place the liters, we need to get rid of moles of NaOH, so we're going to use the concentration to get rid of that. So 0.100 moles NaOH, and that is going to be over liters. And then we are going to times by that 0.03610 liters. And again, we're just going to put that over 1. Okay, so looking at our units, we should be able to cancel out some stuff. So we should be able to get rid of moles of NaOH and liters over here. And then we can calculate what that concentration is. And we get that this is equal to 0.1805 moles per liter. Okay, so this part of the calculation looks the same. The only different part was kind of how we generated some of these numbers. So other thing we do with acid-base titrations is we do acid-base titration curves. So normally one of our 3 experiments when we do our titrations would be to actually generate a titration curve. So when you are doing a titration experiment, wanting to generate a curve, instead of using an indicator in your solution, you are going to use a pH probe. So what you would do is instead of using the Erlenmeyer flask at the bottom, like we did at the beginning, we would use a beaker instead. And that's because a beaker has a nice wide opening. I can stick my pH meter in it, and I can also drop my base droplets into it without it landing on the pH meter. So generally what I would do is I would start by having my acid in my flask. I would record what its pH is when I haven't added anything. Then I would either add 1 or 2 mil increments out of my burette. So I would close the valve, and then I would use my meter to stir it, and then I would check to see what's my new pH. And I would record that. Then I would add another mil or 2, and then I would stop, and then I would swirl it, and then I would record my new pH. So generally when we do that, we're not going to stop when the pH reaches 7, okay? And that's because although in Chem 20 we're always looking for a pH of 7, a lot of times when we do titration curves, that isn't actually what we're looking for. So we're actually going to continue to add base, either until you reach a volume where we tell you you can stop, or where you see that even though you're adding base, the pH doesn't change anymore. It kind of becomes a constant pH. So if you do that, you basically wind up generating a curve that looks like this. So here would be our pH, and here would be the volume of base that we've added. So this would be before I add any base, what's the pH of my acid? Then when I add a little bit, what is it, right? So you can see how we would be collecting a whole lot of data points to generate this curve. So why we want to generate the whole curve is so that we can determine the equivalence point, right? And the equivalence point we said at the start of this was when the moles of acid and base are equal. When you are looking at a titration curve, what you are going to find is that the equivalence point basically happens in the middle of this vertical section, right? That's your vertical. Right here is the middle of it. And it just so happens that that occurs over here at a pH of 7. Okay, and you're going to find that this is always true when I do a strong acid with a strong base, right? And generally in Chem 20, we're doing like sodium hydroxide with hydrochloric acid. They're strong and strong. The other thing you'll notice is that they are both monoprotic, right? Thinking back to when we talked about monoprotic versus polyprotic, it was 1H or 2Hs, or 1OH and 2OHs. So this is what my curve is going to look like anytime I do a strong monoprotic acid with a strong monoprotic base. If I don't, it's going to look different. You're going to see if you take Chem 30, we're going to talk about all those different options. But you're going to find that on a pH curve, I figure out my equivalence point based off the middle of that vertical, which really should be happening at 7. So if I was given this and asked to do a calculation, I would have to look at this and recognize that if this is where my equivalence point is, I need to look down to determine the volume. When I go down, the volume here is 40 mils. So I would be determining that I use 40 mils of base based off of my equivalence point instead of based off of, oh, this was the original burette reading and this was the final burette reading. Okay, sometimes we'll also show you the curve the other way. You should notice that this looks more or less the same. The only difference now is we started with the base in the flask. We ended with acid in the flask. Our vertical is still here. The middle of the vertical is still happening at that pH of 7. And it's still 40 mil for this particular titration because I'm still using the same volume and concentration. Okay, so that basically wraps up all of your stoich. The titration stuff is quite important. It's a very important skill, so please do take the time to watch the video that I link you to for how to actually do a titration. And as I mentioned, when you actually take Chem 30, if you are, please make sure that when we do those titration labs, you've paired yourself up with someone who did actually do it in first semester, so that you're not both kind of standing there being like, oh, I'm really not sure what I'm supposed to do because I haven't ever actually done this, okay? But yeah, so that concludes your stoichiometry unit. Sus.